today to the Medal of the Robotics Seminar Series. He's going to be talking about secure state estimation and controls for dynamical systems and under adversarial attacks. So Paulo did his undergraduate and PhD studies at the IST in Lisbon, where he developed his PhD thesis within the Institute for Systems and Robotics. That's the other ISR. So we have an ISR here. That was the ISR in Portugal.
IST.
Well, IST, but within the IST in ISR, which is an institute. Okay. And it plays a similar role to ISR, but they, that's where he developed his PhD work. And after that, he was a postdoctoral researcher at UPenn and held faculty positions at University of Notre Dame and more recently at UCLA, where he's a full professor and vice chair and also directs the Cyber-Physical Systems Laboratory. So Paulo's contributions to cyber-physical systems have been recognized by many awards, including NSF Career, Ekman Award, and George Axelby Award for the best paper on transactions and automatic control in 2011. And he has chaired and co-chaired several workshops and participated in the organization of many conferences, and also editorial boards, including the IEEE Embedded Systems Letters and the IEEE Transactions on Automatic. So without further delays, I'll
thank you for a nice introduction. So today I'll be speaking about control and security, which is actually a recent topic also for me. And this is collaborative work with Hamza, who's a former master's student that is now studying optimization at MIT with Paulo Tabuada. And in fact, many of the ideas here in this talk have to do with optimization. And it was Hamza that introduced some of these ideas to me. Yasser is a current student. Suhas Digab is a colleague of mine that looks at security problems from an information theoretic point of view. So there will be some ideas of decoding and error corrections coming into this talk because of his influence. Mine is Srivastava is a colleague that is an expert on embedded systems, so there will be some hardware also in this talk, and this was done in collaboration with my colleague. Okay. So one typically doesn't hear about control systems in the news unless something bad happens. And a recent example of that was the Stuxnet virus that was developed to disrupt the normal functioning of these centrifuges that were operating in Iran. So this was a recent example of a cyber attack or an attack launched on the cyber domain that had consequences on a physical system. And since then, people have started paying attention to these issues. And if you look through the popular press, there are many, many other examples of cyber attacks launched on the cyber domain with physical consequences. Even examples of where people go and hack into police cars and can have live streams from what's happening inside the car and can monitor what the police is doing and so on and so forth. Here I'm showing you a video from a project from the Department of Homeland Security where they were trying to assess whether or not by launching a cyber attack on a generator, so this is an electrical generator, whether or not by launching a cyber attack they could disrupt the normal functioning of the electrical generator and try to assess to which extent the power grid is vulnerable to cyber attacks. And well, indeed they succeeded. You see smoke coming out from everywhere. But control systems have been around for many, many years. And so why are we now worried about cyber attacks? And this was not a concern before. Well, one of the main reasons is that they're becoming increasingly distributed, the network. And for convenience reasons, people tend to connect the network whose main objective is to control the system to the internet. And once this link is established, this means that from a very remote location, you can launch a cyber attack, goes to the internet, enters the network that is used for control purposes, and then you can penetrate the system and cause physical harm. There have been, as I mentioned, many examples of these attacks, and even more recent ones.
therefore, there is a need of us starting to think about security of control systems. But people have been discussing how to make control systems resilient also for many, many years. So why is security different from things that have been done in the past? And in particular, why isn't fault-tolerant control not enough to address these issues? Well, in fault-tolerant control, the standing assumption is that there is a fixed number of failures or faults that can occur, and one tries to detect and identify which one of these failures or faults has occurred. But in the case of an attack, we don't know a priori what is the attack that is going to be conducted. We cannot assume that we have a catalog of possible attacks and we're searching just for this, because the attacker comes and does a different attack and we won't be able to defend against it. And in robust control, the standing assumption is that either we have bounded disturbances or some known statistical model for the disturbances. Well, here, if an attack knows that there's a defense, there's some resiliency against bounded disturbances or against a known statistical model, well, we'll pick an attack that violates these assumptions, and therefore, again, we don't have a defense against that. So these type of assumptions that work for these type of issues are not directly applicable when we have a malicious attacker trying to breach the system. And the technical content of the talk will be on how to control a linear system when sensors are under attack. So let me start with the formal setup. I will consider a linear system in discrete time, and I assume that we have 3 sensors monitoring the state of the system. Some of these sensors can be attacked, and I'm going to describe or represent the attack by this attack vector that appears here. And if entry I of the attack vector is different from 0, this means that the sensor is being under attack, and what the attacker is doing is injecting this value into the sensor. When a sensor is attacked, I make no assumptions about what the attack is. In particular, no boundedness assumptions on the signal that is injected by the attacker, no stochastic assumptions, no nothing. I'm simply going to say that some of the sensors are going to be attacked, and the attack can be anything. The only assumption that I will make is that not all the sensors can be attacked at the same time. Okay, so there will be a bound on how many sensors can be attacked, and all the results will have the flavor of if this fraction of sensors are under attack, this is what you can achieve. If that fraction is under attack, perhaps that is impossible. But I will not assume anything either than only a fraction of the sensors have been attacked. The set of attacked sensors, which is unknown, I'm going to denote it by K. And sometimes I'll also use this notation. I'll talk about the support of the attack vector, which is just a collection of indices for which the corresponding entry in the attack vector is different from 0, and this is just a set K. And sometimes I need to refer to how many sensors are under attack, and this will be denoted by Q. So here's an example of a possible attack. This is the attack vector. It's the evolution over time. I'm going to start it on a matrix. And you see here we have a column of zeros. This means that the attacker has not injected any signal on the first sensor, and therefore we're saying that there's no attack on this sensor, there's no attack on this sensor, and there's an attack on sensor 2 and an attack on sensor 3. So the set of attacked sensors is 2 and 3, and the cardinality number of attacked sensors is 2. Okay, now the objective is going to be to design a controller that could be time varying, looks at all the information that has been collected since the system is under operation, and the objective for this controller is to render the system exponentially stable. And this has to occur notwithstanding having an attack on Q sensors. That is, the measurements we're collecting obey this equation, and this vector E has Q elements that are non-zero. There's Q elements that, or Q sensors that are under attack. Okay? And despite this fact, we still want to be able to exponentially stabilize the closed loop system. Now, one way that might be informative of describing the problem is to see this as a game, so that it's clear what are the assumptions that we're making on the attacker and on the defender, and how much knowledge each one has about the actions of the other player. So the dynamics are known to the controller, but the controller does not know the initial state. The attack, however, is omniscient. This means that he knows the plan, he knows what are the values of the sensors, he knows what are the values of the actuators, he knows the control law, and he knows our defense strategy. he knows absolutely everything.
When you say he knows what are the values of the sensor, it means he can keep track of the current readout of the
Yes,
sensor?
of the current readout of the sensors. He can keep track of the values we send to the actuators, and he knows all the algorithms we're going to be running. He has full knowledge of everything. The controller chooses an action based on his past observations. The attacker, before the game starts, determines what is the set of sensors he wants to attack, and then during the game, he feeds values onto those attacked sensors. The controller wants to render the system exponentially stable. The attacker wants to prevent this inequality from pulling. Okay, so this is the objective, and describes who knows what and what are the actions that they can do. Now let's talk about or question a little bit the assumptions and the way I've modeled the problem. Why are we saying that the set of attacked sensors is fixed throughout the game? Well, attacking a sensor takes time. While the attacker is compromising the sensor, we can say that during the time spent, the number of sensors he has access to is fixed. In reality, for the results to hold, I don't really need for the number of attack sensors to remain fixed. All I need is that the time it takes for the attacker to attack a new sensor to be longer than the time it takes for my algorithm to determine which sensors are under attack. Okay? So if he attacks sensors very quickly at the time scale comparable with the defense I have, then I will not be able to know what's happening. If it's slower, then I'm able to determine that, well, he was attacking 3 sensors, later on he started attacking the 4th one as well. The second question is the attacker really attacking the sensors themselves, or the communication between the sensors and the location where we're processing information? Well, in our setup, there is no need to distinguish between these two cases. All we're going to assume is that the information we receive is corrupted. If in fact it's corrupted during the communication or at the sensor level, it will make no difference. We'll just take this information and say it has been corrupted somehow. The other question that arises many times when talking about security for cyber-physical systems is, why can we not use standard techniques from cybersecurity? Why can we not encrypt messages and worry about authentication and all these sorts of things? Well, there are certain attacks in cyber-physical systems for which cybersecurity provides no defenses whatsoever. And I could argue about this, but in fact we took it one step further. We experimentally demonstrated some of these attacks. So if you go under any car that is equipped with ABS, there is an ABS sensor in every wheel, and this is a picture of that. So this part here is actually connected to the wheel that would be on this side. And there's a sensor here, and the way that this sensor works is that it generates a magnetic field. Then this tone ring here rotates synchronously with the wheel, and as these teeth go in and out in front of the sensor, they change the magnetic flux, and then the sensor picks up the modified magnetic flux, and the fluctuations on this flux are going to be proportional to the angular velocity of the wheel. So this is in every car that uses ABS, and this is exposed under a car, meaning that if you go under a car, you're going to be able to see this. So what we did was to build this little circuit that is connected to this PCB strip, where we put the coil inside. We grab this coil and put it in between the sensor and the tone ring. And then here we can do some processing. And the processing we're doing is that we're going to be saying that we want to solve a tracking or output regulation problem while rejecting disturbances. The disturbances are the existing magnetic field. We're going to say, I want to use this coil to measure the magnetic field, and also use this coil to cancel the existing magnetic field and replace it by any magnetic field of my choosing. Why? Because if I do that, then this sensor will be picking up the magnetic field that we are generating, and therefore we can fool the sensor into believing that the velocity of the wheel is any velocity that we want. So here's some experimental results. So this was the original measurements from the original wheel speed. We send this reference in red, saying that I would like the sensor to measure this signal here in red. We put our little kit in operation, and then in blue is what the actual sensor is reporting. So you can force the sensor to track any velocity measurement that we want. Now, why you want cybersecurity to be able to deal with this type of attacks? Well, I have not touched the hardware. You can protect your sensor, but I have not touched the sensor. You can encrypt the message, but the message that is encrypted is already a signal that is spoofed. You can worry about authentication, but the message is coming from the true sensor. So everything is perfectly fine. The issue is that I have attacked the signals before they enter the cyber domain. So cyber defenses work in the cyber domain, but before the signal enters the cyber domain, it has already been spoofed. And
You
therefore,
just have to have physical access.
you need to have physical access. So this is like a
circuits.
physical attack, if you want. I'm attacking on the physical domain.
Or the equivalent of being able to put a little USB thing into a computer that you want to attack.
For example, yeah. And so for these type of attacks, cybersecurity does not provide a defense. And what will you have to rely on? Well, you have to rely on your knowledge about the physical dynamics. Because the hope that you have is that physical dynamics cannot be altered by an attacker, and therefore you should be able to exploit the physical dynamics in some sense as a source of redundancy, as an error-correcting code that is there that you can leverage then to compare measured signals against what the dynamics tells you that the signals, or what the signals should be. And here I'm showing you some animation coming from a car simulator used by the automotive industry. And these are some of the tests that do on the ABS. So this was an example where the driver steers right to avoid ice. And now we attacked one of the wheels and we run the same test. And you're going to see that in this case, because one of the back wheels was under attack, he loses control of his car. And so the little kit that we had has a little radio there. You can go to the coffee shop, you run on your laptop. When this guy that you don't like drives by, you just click, say, launch attack. Laptop communicates with the little radio on the car. Sends spoofing signals to the wheels, and there goes your friend spinning his car down the highway. Okay. By the way, when we tried to publish some of these results the first time, we had a lot of trouble because the reviewers came back and said, "This is actually illegal. Why are you doing such a thing?" Well, I have to make a point that this is possible, otherwise people will not think it's important for us to create defenses against this type of thing. Other reviewers would say things like, "I wish that real bad guys would be as dumb as you, because it's much easier to put a bomb and just blow up the car." Okay, that's not the point. The point is that any sensor of this type can be spoofed, and I don't really care about spinning a car out of control, but if I'm a really bad guy, I can think of all the sensors of this type, where they are, and I can do this in a covered manner. If I put a bomb, everybody knows that's going to happen. If I do something like this, and I'm able to remove the hardware afterwards, people won't know what happened. Okay? But so, in the beginning there was some discussion as to what was the true merit of trying to experimentally demonstrate this type of attacks. All right. So now, remember that I made no assumption about what the attacker can do. He can put a signal that is non-linear, time-varying, no bounds on magnitude, no nothing. So in terms of controller, our controller will also have to be non-linear, time-varying, and extremely powerful to deal with this type of attacks. Well, we can actually prove some kind of separability result or decomposition result. So if we have our plant dynamics as before under attack, and if there exists a controller that is able to render the closed loop system exponentially stable, even though there is an attack on Q sensors, then there exists a decoder, that is, there exists a map that looks at the previous observations and is able to reconstruct the state exactly. So what this means is that I can decompose the problem in two different problems, designing this decoder, reconstruct the state exactly despite the attacks, and then use any controller of your choosing. So I can decouple the state estimation problem from the control problem.
Okay, observability requirement on C.
Yes, but so here the assumption is that if there exists a controller, I can always decompose the controller into a decoder and some controller that assumes that I know the state perfectly. Later on, when I'll give you conditions on how we actually try to construct the observability will come into play. Therefore, the hard problem is really estimating the state from the observations in a way that is resilient under attacks. Designing the controller, we can use any standard technique, then assuming that we have access to the state. So the real hard problem is to design the decoder. Okay, so then this leads us to error correction. So since we're designing the controller, we know what the input is, and because we have linearity when trying to estimate the state, we can cancel the effect of the input. So to simplify things, I'm just going to assume that the input is 0, because it will make no difference at the end. And now I'll say that the decoder is just this map that looks at observations and produces an estimate of the initial state. And I will say that the decoder corrects Q errors after T steps if it looks at a sequence of observations of length T, reconstructs the initial state exactly, even though Q sensors are under attack. So these Q errors, this doesn't mean Q errors in total, this means that at every measurement, at every time instant, Q sensors have been under attack. So the total number of errors would be Q times T. Okay, so at every instant, Q errors are present on my measurements. And we will say that Q errors are correctable for a pair AC if there exists a decoder that can correct Q errors. Now, how does this relate to observability? Correcting Q equals to 0 errors is equivalent to observability, because that simply means that from my observations, I'm able to recover the state. Now, I'm trying to do something harder, because not only I am able to recover the state, I'm able to do so even though there are errors in my observations. So one should expect that the condition that I will need is something stronger than just observability. So here's a characterization of when Q errors are correctable after T steps. For every state, I'm going to check this condition, and what this condition does is that I compute Cx, Cax, and so on, and Ca raised to T minus 1x. I look at the support of these vectors, take the union of these, check the cardinality of this set, has to be bigger than 2Q. So let me try to give you some intuition as to what this condition is telling us. That when we look at these matrices, they have to spread the components of the state. Here's an example of a good pair. Take the A matrix to be a permutation matrix. Take C to be the identity. So we have one sensor per entry of the state vector. And let's assume that this was my state vector. And so what I really want to know is what is x1. When I make my first measurement, because C is the identity, I measure x1, I measure 0 and 0. If there's an attack here that corrupts the value of x1, then the next time step, the dynamics is such that it moves x1 to the second position. And then when I make a measurement, I'm also measuring this. So if the attacker attacked this measurement here, I have another chance of looking at what x1 was. If the attacker attacks this, I have another chance of looking at what x1 was. So if the dynamics gives me enough redundancy, so that over time I get the same measurement or correlated measurements over time by looking at the same sensor information, then there is hope that I'll be able to be tolerant against some attacks. An example of a bad pair is A being the identity and C being the identity. Because in this case, the dynamics is not giving me any redundancy. It's not changing the state whatsoever. So if there's an attack on a sensor, there's no way I'm going to be able to recover that information because the dynamics is not helping. Now, this condition is not easy to check because it says that I have to take every state vector and check this. And there are infinitely many state vectors, so there's no way I can actually check this condition. But we can use it to give us interesting or important information. One of the things we can infer from this is that the number of correctable errors does not increase beyond the dimension of the state. And this just follows from the Cayley-Hamilton theorem. Because the vectors that I obtain here, the dimension will not grow beyond n, and because I'm looking at the support, the best case I can have is that having support being all the vectors being supported on all their entries. It also tells us that no more than p over 2 errors can be corrected. So p is the number of sensors. there is no way I can be resilient to an attack more than half of the sensors. So this comes from all these vectors being on the image of C. Image of C has dimension P. So in the best case, I'm going to have here vectors of dimension P. If I have non-zero entries everywhere, this cardinality is at most P. So I have that P bigger than 2Q. Therefore, if an attacker attacks more than half of the sensors, there is no way that we can recover. Yes?
Is there intuition on this 2Q?
Why the 2?
The intuition?
Yes, so so if you forget about dynamics, there's a very simple example. Say that you have half of your sensors are under attack. And say that they're all exact copies of the same sensor. So you look at the measurements, you know that they should all be reporting the same number. And you see that half of them is reporting one number, the other half is reporting another number. You know that half is lying, but you don't know which half. So it's the same thing that happens here. You'll be able to know that there is an attack, but you cannot reconstruct the state. As in this example, you know that half of them are lying, but you have no idea which half. So that's where the Q comes from. So as I was mentioning, this is a fundamental limitation. Independently of which algorithm we use to try to reconstruct the state, we will know there's an attack, we will never know what's the true state. In the sense that the attacker always has a strategy that will confuse us. We'll always be confused about what is the true state, even though we know that we're under attack. So if he attacks more than half of the sensors, there's nothing we can do. How about if he attacks less than half of the sensors? Can we reconstruct? Here's a proposition that is easy to prove. For almost all pairs, the number of correctable errors is maximal and equal to half of the sensors. Now, this is easy to prove, but not really interesting, because in practice, I don't have a generic AC pair, I have a concrete one. And what I'd really like to know is, if you give me a concrete pair, what is the number of correctable errors? There is one particular case that can be efficiently checked. If the A matrix is diagonalizable and the eigenvalues have different magnitudes, then what I can do is that simply compute the support of C times V for every eigenvector of A. And if this is bigger than 2Q, then we can correct Q errors. So now this condition is very different from the previous one, because here I have to test this for every state vector, here for every eigenvector, and there are only finite elements. So this is something I can easily check. At the end of the talk, I'll come back to this. I'll give you an if and only if condition, which nevertheless can be checked. So it will be you have to do finitely many computations, but it's still an NP hard problem. So it's hard to check, but only finitely many computations are required, whereas here we're doing infinitely many.
If it's a linear problem, can you give me some information as to why you can't pick a
Why is it-
basis set?
Why is it hard?
Why you don't know, why you can't pick a basis set
Oh.
for the Castle to support?
Yes, because the way that the attack, so the space of attacks is not a vector space. The space of attacks is a union of vector spaces. So the cardinality constraint I have, if I say that only two sensors have been attacked, then you're going to have to look at all vectors that have at most two non-zero entries. And the collection of these vectors is not a vector space. And therefore, typical ideas one would expect do not hold there. Okay. Now, another question is, okay, so I'm given a specific pair, but then maybe the number of errors I can correct is not maximal. Is there any way I can improve resiliency by using control? Here's one result along that direction. So if the pair AB is controllable, and we want to do pole placement, so you give me your desired location for the closed loop poles, and I'm assuming that they have distinct magnitudes, then I can always find a feedback control law that places the poles at the desired locations and makes the new pair AC maximally resilient against attacks. That is, I can worry about two things at the same time, doing pole placement so that I meet my performance constraints and improving resiliency up to the maximal limit that can be achieved, which is P over 2. Now, the problem with this result is that this makes sense if the implementation of your control law is not subject to attacks. Because typically, when you implement a control law, you need to rely on measurements. And if this control law is based on measurements that have been corrupted, then this result is no longer true. So if you can do some local feedback that is not subject to attacks, that indeed you can improve resiliency, and then maybe you are also sending information from sensors to, say, supervisory control at some different location, then that local loop, if it's not subject to attack, so you can improve resiliency. If it's subject to attack, well, it doesn't work because you would be doing control based on faulty measurements. So far, I've only talked about being able to correct errors, not being able to correct errors, but I have not talked about how do we actually reconstruct the state. Okay, can we actually do it? Is there an efficient algorithm that will allow us to solve this problem? So we've received a few observations, finite sequence of observations, and we're going to reconstruct the initial state. Now, the solution I'm going to propose involves estimating many or several of these quantities at the same time. So I'm going to show you that the problem is not harder because of that. I'm going to show that estimating the initial state, the attack, or the set of attack sensors are all equivalent problems. So it doesn't matter which one we try to construct. So if I know the initial state using the dynamics, I know the state at every time instant. And if I compare what I observed with what I was expecting to observe, the mismatch gives me the attack vector. So if I know the initial state, I can also know the attack vector. If I know the attack vector, I also know its support, which is the sensors that are under attack. Therefore, I also know the collection of attack sensors. And if I know the collection of attack sensors, I can simply throw away those measurements, use the remaining measurements, and reconstruct the state. So if I know, okay, the set of attack sensors, I also know the initial state. So these are all equivalent. So it's no harder searching for one or searching for more than one. And so my student Hamza, really being in love with optimization, he told me that, well, what we should do is to phrase this as an optimization problem. So we should search for the initial state as well as for the smallest set of attack sensors that is compatible with the dynamics. That is, when I look at my observations, and the observations I expect to see based on my estimate for the initial state, if I look at its support, well, the support is exactly contained in Q, in K, which is the set of attack sensors I'm estimating. And I want to do this while trying to make the set of attack sensors as small as possible. And I told him,
Sorry,
yes,
we just lost me. What is the reason for minimizing the cardinality?
Because if I say that all sensors are under attack, the problem always has a solution. Okay? But that's not an interesting solution. I really want to know what is the smallest set of attack sensors that explains the data I'm seeing. If I let it become large, then there's a trivial solution. Because if you attack all the sensors, you can make anything you want compatible with the dynamics, essentially. So this is our decoder formulated as an optimization problem. And then I asked my student, okay, so sure, I'm sure everything can be written as an optimization problem, but how good is this decoder? And if Q errors are correctable, then this decoder can correct those errors. So in some sense, this decoder is optimal because there's no other decoder that is strictly better than this one. But this is an NP-hard problem. And the reason why this is an NP-hard problem is because we're maximizing over the cardinality of this set. So if you try to solve this in a naive way, you'd say, let me see if by attacking just one sensor, I can solve the problem. And then you say, well, I'm going to pick sensor 1, see if what I've observed is compatible with the dynamics. Let me try sensor 2, and so on. Okay, maybe I couldn't solve it. So now I'm going to look at all subsets of 2 sensors. And I'm going to test all of this. Now all subsets of 3 sensors, and so on and so forth. So this is a combinatorial problem. And then when I told my student, well, this is a combinatorial problem, it doesn't make any sense. But my student, before coming to UCLA, he had worked with Emmanuel Candes at the time when he was still at Caltech, and he told me, oh no, Paulo, there's a standard way to solve these things. what we have is an L0 optimization problem, and then everybody does a relaxation mixed in L1 optimization, and this is standard. Everybody does this, so we should also do it. I said, okay, I want to see that. I want to see how you do those things. So for those of you that know how to do this, this what I will say now will be something fairly obvious. For those of you that have not been exposed to these ideas, I'll just give you a brief intuition on how this can be done. So let's put on a matrix as column vectors all our observations, call this capital Y. Here we put the dependence of the observations on the state. I'm calling this phi times x, the state. And here I'm going to put all the attacks, and I'm going to call this capital E. Now, if I look at my matrix having all the attacks, if you remember, when a sensor is not attacked, I would have a row of zeros. So if I count the number of rows that are non-zero, I'm counting the number of attacked sensors. Okay, because a row that has entries that are different from zero corresponds to a sensor where information is being injected by the attacker. So if I count the non-zero rows, I'm counting the number of attacked sensors. Therefore, I'm going to say that the number of non-zero rows is the L0 norm of the matrix E. And now our previous decoder is basically solving this optimization problem. If I compute my observation, the difference between the observations and what I was expecting to observe, I get my matrix of attacks. And if I now count the number of non-zero rows, I'm counting the number of attack sensors. So what I want is to find the state that leads to the smallest number of attack sensors. So I'm minimizing the L0 norm of this matrix by searching over possible initial states. That's what I'm doing. But then, because it's the L0 norm, this is a hard problem, so we replace it with the L1 norm. How do we do this? Well, rather than counting non-zero rows, now I'm going to say that in order to know if a row has zero elements or not, I'm going to pick some norm, LR, and I'm going to use this norm as a measure of how different is the row from being zero. And therefore, before counting the number of non-zero rows was summing the number of non-zero rows. Now I do the same thing. I sum the values of LR, where LR is applied to every row. And this gives me this L1/LR norm. So the magnitude of a row is now measured by this LR norm. And this is an idea that has been put forward by Candace, as I mentioned, and Tao at UCLA, Donoho at Stanford, and so on. And so we tested this in some examples. I really wanted to see if this thing actually works. So we generated randomly some pairs AC, and here's a plot telling you if we can actually detect the attack, or if we fail to detect the attack, then you see there's a transition here, and the transition occurs around 10, and you see that we have 20 sensors, and the condition we had was that if the attacker attacks more than half, it's impossible. Half is 10. So around half, things start to break. We would expect that for more than 10 attack sensors, we would not be able to do it. In fact, a little bit before, we also start making mistakes. That's expectable because what we did was a relaxation. We are not solving the original problem, we're solving a relaxed problem. And so there's the question as to when is this relaxation actually giving me a solution to the original problem. We also tested on a real example from an IEEE, the 14 bus system. We get the same type of behavior, where, except that the transition is a little bit slower, not as abrupt as before. And so now the question would be to study when is this relaxation working. We did derive some conditions telling us when the relaxation gives a solution to the original problem. But I was not too excited about this way of solving the problem for several reasons. The first one is, so let's first review exactly what the solution is. I collect T measurements, solve an optimization problem to get the initial state, then use the dynamics to go from the initial state to the current state, and then I'll do control. Then I'll get the new measurement, solve another optimization problem. Well, this has a lot of problems. First, I don't like this idea of throwing away all the computations I did when a new measurement comes and then solve a new optimization problem at every time you see. This sounds like not a very smart thing to do. Moreover, if I just use an off-the-shelf optimization engine, this would be slow. At every time step, I know I need to control fast, and at every time step, I'm solving an optimization problem. Second, it would be hard to give real-time guarantees, because if I want to implement this on an embedded microcontroller, I need to know exactly how much time is going to take for this optimization problem to give me my estimate. And this is an optimization problem. I may not know how many steps I need to converge. But more importantly, if I want to make things secure, I would never compile a piece of code that somebody else would give to me saying, oh, I have this optimization engine. Why don't you just link this library to your code and do it? Well, I would never put a piece of code from a third party in my secure state estimator. Even if I end up using exactly the same algorithm, I will have to re-implement it to make sure that there's no Trojan horse, there's nothing funky coming in when I link a third party library. So how do we solve these problems if we would not have security concerns? Well, we would use an observer or maybe some Kalman filter. So can we do something like this? Can we devise an observer that is resilient to attacks? And so you see that even though I'm trying to move away from optimization and I want to do an observer, my observer will look like a specific scheme for solving optimization problems. So here's what I'm going to do. I'm going to slightly change the dynamics, because now, rather than try to just reconstruct the state, my state vector z will also contain the attack vectors. So now I'm going to try to reconstruct the state of the plant as well as the attack vectors. Therefore, I have to change the A and B matrices. As observations, now I have my sequence of observations, so I also have to change my C matrix, and now I'm calling it Q. So these are straightforward extensions for the matrices, so that I'm now dealing with this extended vector. There's only one non-obvious thing, which is the fact that the attack vector is unknown. So how can it be part of the state? How can I have a model that describes what the attacker is doing? If it's unknown, I cannot model it. So what we do is to say that, well, the attack is the mismatch between what I observed and what I was expecting to observe. What I was expecting to observe, I can use the dynamics to rewrite it as a function of the state I have available to me and the inputs I've been receiving. And also the measurement at time t. So what I can do is that if I take the measurement at time t as being part of the input, then I can have an equation for the dynamics of the attack. So essentially what I'm doing is that I measure make observations at time t, but I'm pretending that I'm time t minus 1. So at time t minus 1, I already made an observation saying to the future, which I use it as an input for my filter, pretending that I'm working one step back, one step in the past. Okay, so in this way, I have a model for my dynamics. And now, a typical Luenberger observer would be a copy of the dynamics plus a term, a correction term, based on the mismatch between my expected observations and the true observations. Now, let us rewrite the Luenberger observer by, rather than doing things in one step, doing things in 2 steps. Here, I simply look at my estimate and correct it using the measurements that I have. And here, I correct it using the dynamics. I just split it into 2 steps. Corrections based on measurements and based on the dynamics. Now, if I try to do something like this, I immediately face the problem that the attack vectors, which are part of C, if they're given by these dynamical equations, they are not supported on an attack set with a certain cardinality. That is, I will not have 0 elements appearing on my attack vectors because there's no way that these dynamics would enforce the presence of those zeros. So if you want to enforce the presence of those zeros, we can add an extra step, which is simply a projection on the constraint set. I'll simply go there and say, no, I'll force a certain number of entries to be 0. How? What I will do is that I'll pick the smallest entries and set them to 0, and therefore I am forcing this constraint to be satisfied. And now, if you look at the measurement step and interpret it as a gradient step, so if you do gradient descent, you have exactly the state here, and this would be the gradient of your cost function. So if you think of this as being a gradient step, this algorithm is no more than an optimization algorithm called projected gradient, or hard thresholding, or proximal gradient. There are many names that are given to this type of algorithm. And this is no more than an algorithm to solve an optimization problem with sparsity constraints.
That projection step though involves some kind of sorting, right?
Yes, you search for the smallest elements, yes, and then just set them to 0. And we looked into the literature to see when is this type of algorithms guaranteed to converge. And the conditions that are available are conditions on the measurement equation, and they are conditions that are too strict to be useful for our case. So let me explain you why. So these algorithms are used in the context of compressive sensing, and in that context, this is the measurement equation. And the typical results say that if this matrix here is nice, nice means some bounds on the restricted isometry property of this matrix, then this algorithm is going to converge. And in that setting, it's okay to talk about this matrix being nice because this is your measurement operator. If it's not nice, you have to pick a different one. You have to change the way you're making measurements. In our case, this Q matrix is completely determined by A and C. And there's no way we can change the A matrix. We don't get to design the A matrix. And the C matrix, it's also not the case that we're going to change the sensors. In the compressive case, the idea is that you have too many measurements and you can always subsample. Do something smart by getting rid of some of the data you have available to you, and you have that freedom. Here, we don't have too many measurements. So we also don't have the freedom of changing C. So what we did was we opened the proof of these results. And inside the proof, there were tons of inequalities and a bunch of stuff. But then one looks carefully and one sees, oh, what they're doing is that they pick the Lyapunov function, and they see if this Lyapunov function is going up or down. And then they prove that whenever they do the gradient step, the Lyapunov function is coming down. When they do the projection step, the Lyapunov function goes up. And then they check when is the decrease caused by the projection going to be bigger than the increase caused by the gradient, bigger than the increase caused by the projection. Well, there's a certain condition. That's exactly the assumption on their theorem. So what we did was to say, we can do something like that. We can, rather than just taking one step, because those would be the conditions that they have, we can take multiple gradient steps until the increase caused by the dynamics and the projection is compensated by the decrease caused by these multiple steps I'm taking there. And because we had done some work on event-triggered control, we said that, well, this is very much in the spirit of event-trigger. So I'm detecting when this event occurs, which is the event stating that it's okay now to do time of data and projection. And so I have this rule that in execution time is keeping track of this and decides what should we be doing, gradient descent or time of data and projection. And we call this the event-triggered projected Lumberger observer. Okay, so when is this algorithm going to give us the right results? And for that, to characterize that, let's talk about observability. So I will say that the pair AC is Q sparse observable if by replacing C with the matrix C prime, and C prime is obtained from C by removing Q rows from C, what I obtain is still observable. This essentially means the following. If I go to my sensors and remove Q sensors, just look at the remaining ones, it's still observable. And this has to be true no matter which Q sensors I remove. So if this is true, if I'm always observable, no matter which Q sensors I remove, then I'm saying that this system is Q sparse observable. Now this is clearly a necessary condition, because if Q sensors have been under attack, I have to be able to discard them and with the remaining ones reconstruct the state. So this is clearly necessary, but it turns out to also be sufficient. So if I have a Q sparse observable linear system, then the observer I just described, whenever I pick the Lumberger gain to be Q transpose sigma, sigma you can think of the time step in an optimization algorithm, and satisfying this bound, so time step cannot be too large, then the algorithm is guaranteed to reconstruct the true state and the true attacks whenever the number of attack sensors is no bigger than Q. And so Q is the same that appears there on our research. So in particular, for any pair AC, Q errors are correctable if and only if the pair is 2 Q sparse observable. So remember, before I had a condition that I said I cannot check it because it says for every state I have to check something. That's impossible. Then I had another one that said, oh, only eigenvectors, but A has to be diagonalizable. So this one sits somewhere in the middle, in the sense that no diagonalizability assumption on A, But I have to check this. I have to check if this condition is satisfied. But this condition is also has also a combinatorial flavor, because I have to build from AC all these pairs of A, C primes, and then check observability for all of these pairs. Okay, so it's much harder to check than just looking at the eigenvectors, but no assumptions on it. So it somehow sits in between the other two conditions we had before. Now, this algorithm is always guaranteed to work, but I have not talked about the speed of convergence. Speed of convergence actually depends on the observability. So, for example, looking at singular values of the observability gradient. If the system is strongly observable, converges quickly. If it's very close to being unobservable, converges very, very slowly. So, the previous result that I had in terms of relaxations, there, the problem we were looking at was I do a relaxation, when does it give me the solution to the true problem? Here, I always get the right solution, and the price I have to pay is that sometimes it may take a long time to get to the right solution when I'm very weakly observable. So, does it actually work? And in collaboration with some of my colleagues at the University of Pennsylvania, we've deployed this on a Cadillac SUV. So this computer is connected to the CAN bus of the Cadillac SUV, and messages that contain the velocity of the wheels are being attacked. Here you see the ground truth velocity. Here we are running two estimators, one that is robust with respect to attacks, one that is not robust with respect to the attacks. Now is launching an attack, and you see that one of the estimators starting to go up and down because the measurements are being spoofed, whereas the other estimator, I don't know if you can see very well, that is resilient against attacks is giving us something very, very close to the ground truth. So it actually works on real systems. Okay, so let me tell you now a little bit about the things that we're currently investigating right now. So why are we looking at attacks on sensors? Why don't we attack actuators? Well, if you're an attacker, you should go and attack an actuator. Why? Because if you attack an actuator, you immediately inject energy into the system, you immediately make it do something crazy. Whereas if you attack a sensor, the defender can still detect that, throw that information away, and still control the system. If you attack an actuator, there's essentially no defense but to shut down that actuator. Because you're just injecting energy into the system, you can make him do something very, very foolish.
So there's also an intermediate thing, or maybe you don't distinguish as intermediate, but you could attack the gains.
You could attack the gains, and I will talk a little bit about that. We're not looking at attacking the gains, but I'm looking at letting the attacker entering the platform where I'm computing, doing state estimation and the controller, and letting him change the code there. I'll talk a little bit about that. So the other thing is, in my modest opinion, there's no such a thing as a linear system. All the systems are non-linear, and you have to make all kinds of assumptions to work in a regime where the linear approximation is valid. But now if you have an attacker, maybe what the attacker will do is to try to make you move to a region where your linear approximation is not valid, where linear assumption is not valid. So we're trying to go to the nonlinear case and develop these ideas in the nonlinear case. There it's much, much harder. And the reason why it's much harder is because for linear systems, there are two different concepts that become the same. For linear systems, stability towards an equilibrium and stability towards a trajectory, that this trajectory is converging towards another trajectory, they turn out to be equivalent. In the nonlinear case, these are different things. And observability is the problem of, can I design a dynamical system whose trajectories are converging to the trajectories of the real system? And that is much harder than designing a dynamical system that converges to an equilibrium. And therefore, many of the things that we know for linear systems, then they break down when we go to the nonlinear case. How about noise? Everybody always asks me, oh, but you didn't consider noise, and if there's noise, maybe the attacker will launch an attack that can be statistically confused with the noise, and then you don't really know if it's true noise or the attack. Well, my standard answer is, if the attack can be confused with noise, that's okay, because when I design the controller, I design it to be resilient to the noise. And so if the attack behaves exactly like the noise, my controller already handles that. Still, we're trying to give some characterizations of how resilient this type of techniques are when there are noise. So now let me go back to your point. What happens if the attacker actually has access to the microcontroller where we're doing state estimation and control? The approach we're taking to this is the following. In order for the attacker to do something useful with the platform, he needs to have access to the state. So rather than protecting the controller, we're again protecting the state estimation process. And what we're doing is to say, and this is something that is known in distributed computation, is rather than having a single location where we're doing state estimation, we want to distribute this over multiple locations so that no platform knows the state, but collectively they all know what the state is, in the meaning that when they send information to the actuators, only at that point the actuator is able to recover the true input that is to be sent, but nobody has access to the state. Nobody knows the state. So now if the attacker attacks one of those nodes, he will not know the state. If he attacks 2 or 3, he will not know the state. And in order to reconstruct the state, he has to attack a large fraction of these nodes. And the assumption is that it's hard for him to penetrate a large fraction of the nodes, and therefore you're improving resiliency by not having any single location that has knowledge about the state. And therefore, if he wants to change the gains, well, you'll not know the state to which gains you would like to apply to. And with this, I would like to end by thanking my students and collaborators at UCLA, collaborators at UPenn, NSF and DARPA for funding some of this work, and Professor Nuno Martins for inviting me to be here, and all of you for attending my talk. Thank you.
So I have a question. So on the example we did, where you applied the settings to the car, that is a running observer. But in the formulation that you gave at the beginning, from which you developed the entire theory, was basically stabilization to zero, and you mentioned, why certain things, certain notions of stability are all equivalent. But really what you're doing there in the analysis, in the theory, is recovering the initial condition, right? So when you have this kind of running, if you're running the estimator for a long time, what is exactly that you're doing? You're estimating the initial condition with some delay, or do you then propagate?
So if you do the optimization-based approach, we would estimate the initial state with a delay. But then we would actually not rest on that initial state. We would use that to know which sensors are under attack, pick the remaining ones, and then use any observer you want to actually estimate the state.
Okay.
So even though we would also recover the state, in practice, that's not the best state estimate you get, but you know which sensors are under attack, and that's what you do. On the other one, on the Lumberger observer, we reconstruct the state with just one time step delay. And so we would just directly use that state for control directly.
So you use that basically just to figure out what are the inputs,
What are the inputs? So this is the reason why we wanted to go to a, let's say, recursive estimator, because we didn't like much the idea of doing optimization to know which sensors are under attack, throw away information, use another estimator then to propagate things forward, and then at the next time step we get a new measurement, recompute everything again.
Is there any type of attack that you could make that would not be detected?
If it's more than half of the sensor,
No.
no, you mean, no, more than half we still detect there's an attack, we just don't know what the state is. That could not be, yeah. So Francesco Bullo and his students looked at this problem, and this has to do with zero dynamics. So essentially, the system needs to have non-trivial zero dynamics, and then the attackers hide in the zero dynamics. And so, and he has a characterization of exactly what are the type of attacks that you're not able to detect because of that.
That was the possibility.
Possible, yes, yes.
So in the beginning that we assume that we are truthful to the adversary, do we know the same thing from him? Do we know that, do we know his worst case strategy given our search to him?
No. So to prove this result that when we attack more than half of the sensors, it's impossible to know the state, we construct a strategy that confuses us, but we didn't think about what would be the worst possible strategy for us. So we have one example of a strategy for which there is no defense, but we didn't consider the problem of what would be the worst strategy that he could use, worse from the point of view of the defender. No, we did not look at it.
So the problem of Q observability determination, or 2Q observability determination, you pointed out, is also a combinatorial problem. So is there some relaxation for that as well that you're considering?
No, we haven't looked into that. I have kind of mixed feelings into this way of looking at these problems, because in some of the results have this flavor. You have this hard problem, you do a relaxation. Now, when is the relaxation going to give you the true solution? Well, there's actually another optimization problem you can solve that will tell you when this one is giving you the right. And then you build these hierarchies and hierarchies of optimization problems. And the reason I have mixed feelings about this is that I don't get a lot of intuition about what's happening by knowing that an optimization problem does the right thing depending on the solution of another optimization problem. So no, the answer is no, we didn't check. For the examples we worked with, the number of sensors was small enough that this was not a problem. But if you think of something like power grids or a chemical plant where you have hundreds of sensors, then that is clearly a problem.
In optimization from sample data, one encounters something very akin to what you're talking about, and people usually don't articulate it quite the same way, and that is, if you have a data set, you want to fit, but you also have a way of imposing a regularization, so that it's a penalty function term. But then there's always a parameter in there, there's a penalty parameter. So in addition to solving optimization for a fixed penalty parameter, you have to also solve the cross-validation problem, which is another optimization problem. And then only based on that would be able to, so at least there the hierarchy stops at a certain level, but I think I can build more.
Right.
Thanks a lot.
Can you tell me how many sensors do you have in the car, and how many do you have?
In the car, we had one sensor per wheel. I think there was also GPS that we were using, and I think we were attacking 2 wheels.
So
Because
2 out of 5.
2 out of 5, because it has to be less than half. Half is never, it might not be an integer number, so strictly less than half, so we have to attack 2.
It's probably also having accelerometer.
But we were not using accelerometer, we were using the velocity measurements of the wheels and GPS.
And you would probably use the accelerometer in deciding whether the wheels are wrong.
We could use the accelerometer as well, yes. So typically the way they do it in ABS is that they compare the velocity of the wheel with the velocity of the car itself to determine if the wheel is slipping or not.
Would you include the brake pedal sensor as well? Would you include the brake pedal sensor as well?
No, because that does not give me information about the physical dynamics. Right? So I would expect that when I press the braking pedal that the velocity would decrease. Whether or not that happens can be easily violated because now you have brake by wire. Right? So there's no physical law that gives me a strong correlation between the angle of the braking pedal and the velocity of the wheel.